Well, hello, welcome to this spectral analysis where I will use IR, carbon NMR, and protein NMR data to determine the structure of an unknown compound. And today we will apply fundamental techniques in structure analysis to solve a real-world organic chemistry problem. So the molecular formula we have been given is C10H12O. Using this and our spectra, we will go through these steps. I will first calculate the degrees of unsaturation, or the DU, to determine rings and or double bonds. I will then analyze the IR spectrum to identify functional groups. I will interpret the carbon NMR spectrum to determine carbon environments. I will also break down the proton NMR spectrum to identify hydrogen connectivity and splitting patterns. And then finally, I will propose the final molecular structure and confirm its correctness. So let's begin. First, we will use the molecular formula to determine the number of degrees of unsaturation, or the DU. This will tell us how many rings or double bonds are present in our molecule. So the formula for DU is right here. So it is 2 times the number of carbons plus 2 minus the number of hydrogens. So based on the molecular formula of C10H12O, I plug in the numbers and the values, complete the math, and here we get a number of 5. So a DU of 5 suggests the presence of multiple rings and or double bonds. Since a benzene ring alone accounts for 4 DU, the remaining 1 DU indicates an additional unsaturation, likely a carbonyl functional group. Next, we will analyze the IR spectrum to identify functional groups. Okay, and so here are the peaks, here are the data, and so right here, the the carbon-oxygen double bond stretch at about 1700 is strong, and it confirms a carbonyl functional group, likely a ketone. The carbon-carbon double bond stretch between 1475 and 1600 further supports the presence of a benzene ring. So these findings here suggest that we are dealing with a benzyl ketone, but we need to confirm that with NMR data. So the carbon NMR data here helps us to determine different carbon environments in the molecule, and this is what we observe right here, and data. So the 210 parts per million peak confirms a ketone carbonyl. The 120 to 160 parts per million range confirms an aromatic benzene ring. Additionally, we also see aliphatic carbons at about 37 and 51 parts per million, which suggests a substituted carbon chain next to the benzene and ketone groups. Moving on to proton NMR analysis with this spectrum. The spectrum provides detailed hydrogen environments, information on detailed hydrogen environments. So we will analyze each region. The multiplet here at 7.2 parts per million with a 5H integration confirms a monosubstituted benzene ring. The singlet at 3.6 suggests a benzylic CH2. And then here, this 2H integration between 2 and 3, roughly 2.5 parts per million, and a triplet at 1 parts per million match a ethyl substituent. So, based on all of that data, the final structure that I am proposing is this structure right here. And its IUPAC name would be 1-phenyl 2-pentanone. And I believe that this fits because the Du equals 5 and indicates a benzene ring and a ketone. The IR spectrum confirms a carbon-oxygen double bond ketone and aromatic ring. The carbon NMR shows a ketone at 210 parts per million and benzene carbons at 120 to 160 parts per million. The proton NMR confirms a monosubstituted benzene, a benzylic CH2, and an ethyl chain. So everything aligns with this compound being 1-phenyl 2-pentanone, making it the correct structure.